it's beneficial even if nobody has global position information.
So, and then flying in and out of a warehouse, for example, Amazon warehouse.
It's anticipated that in a serious conflict that GPS would be eliminated.
Welcome to the Tech Transfer Podcast. I'm Dave Brown. I'm here with Professor Tim McLain, and we are going to talk about a UAV technology that is good for manning those situations where there's no GPS signal. So, Tim, what's the technology and what problem were you addressing?
So the technology, we call it broadly relative navigation. We've applied it to systems, just single aircraft systems, but in this case to multiple aircraft working together. And the basic idea is that if the aircraft can communicate with each other, then there's information contained in that communication about how far apart the aircraft are from each other. If they're in a situation where they don't have GPS, they can exploit that inter-vehicle range measurement to help each aircraft figure out better where they are in the absence of GPS.
Okay, so this could be any kind of aircraft probably. I'm picturing small drones. And when they communicate with each other, do they know how far apart they are because of how long the signal takes to move?
Yeah, that's the idea, is that there's a technology, it's called ranging radio, and basically that whenever a communication transmission happens, there's some time of flight processing that's done that gives basically range information.
Okay. So a group of drones or whatever vehicle are communicating with each other, and they're also doing some mapping, right? How does that part of it work?
So in a GPS-denied scenario or even degraded GPS scenario, the individual aircraft can use onboard sensors such as accelerometers, rate gyros, cameras looking at the terrain or the environment below, and they can use features in the environment, imagery along with these other sensors to basically figure out how they're going. It's called visual odometry. They can figure out how they're traveling over if there's known landmarks that they see, they can figure out where they are relative to those landmarks. And if those landmarks are in known locations, then they can figure out where they are in the world from using camera information.
Well, that's great. And so I should note that we have a patent that's about to issue on this technology, and it will cover, among other things, this mapping function. When you say that it's they're noticing like known terrain, this is not necessarily like marks on a map. It could just be features that they recognize, right?
That's right. So it could be just visual features that are distinct in the imagery, or it could be that they're known landmarks. So they could be a building, a certain building, where referencing an existing map, the aircraft could know where it was relative to that.
Okay, so let's go through some scenarios just to see how this would look in the real world. So one thing that immediately comes to mind is military applications. If you had drones flying through a canyon or something, they might lose the GPS signal because of the canyon walls, but they're talking to each other and mapping the terrain. Is that a realistic thing that could happen? Yeah,
that's, I think, a concept. In canyons, of course, GPS can be degraded or lost altogether. So that's a scenario. Another scenario that's perhaps more likely is jamming of GPS or just all-out obliteration of GPS.
Oh, that's interesting. So in a military situation, there'll probably be some kind of jamming?
Yes. Yeah, so the idea, I guess, would be that if you had a group of vehicles that were flying as a swarm or a group, it's important that they know where they are. And if they were to lose GPS, but they had the ability to localize relative to the terrain or as they were flying, and by localize I mean know their position relative to just visual features, that they could use this visual odometry idea to figure out basically how they were moving with respect to the terrain and have some sense of where they are. However, when you're doing techniques like this visual odometry, you have sources of error. Like typically you would say that the heading error of the aircraft, the knowledge of the aircraft, the knowledge of the aircraft's direction that it's flying is not as precise as you would hope. And as it flies, doing this visual odometry, it accumulates significant amounts of error, and so it can drift off course, basically.
Oh, sure.
So if you have multiple aircraft that are drifting off course, so to speak, but they're able to communicate with each other, you can basically get rid of some of that drift or a significant amount of that drift error from these inter-vehicle range measurements. Furthermore, if any one vehicle knows where it is, all of the vehicles can know where they are by communicating their relative pose or relative range or relative bearing. All of that sort of information can be exploited. And they need to also be able to communicate where they are at the time of their communication.
So in a scenario like the canyon one we're talking about for a second, could you have, like if it's a group of drones, could you have one of them flying much higher, so it's not even in the canyon, but it has a clear line to communicate with them? Would that solve the problem?
Yeah, in some situations, an aircraft flying high above the canyon would have GPS and could provide global information to the aircraft below. But this concept, it's beneficial even if nobody has global position information. It can, in essence, take out that drift error that I was talking about, where the aircraft might not know exactly where they are in the world, but they will know where they are relative to each other. And their uncertainty about where they are in the world will be smaller by exchanging this relative range information than it would be if they didn't exchange the information.
Got it. And so another, I think, realistic application would be within cities. Like if you're flying between skyscrapers, then you're going to lose the signal or it's going to be distorted somehow.
Yes.
Is that another place to use it?
Yeah, I think essentially anywhere that you have degradation of GPS or loss of GPS, these sort of concepts could be exploited. Yeah.
So, and then flying in and out of a warehouse, for example, Amazon warehouse or whoever, that could work. I've also wondered. So people talk about having like UAV, well, they're not UAVs, but taxis, like air taxis. If you had vehicles, like large vehicles that aren't flying in a swarm, but they are all in the same area, would they still be able to do this?
Yeah, I think the key thing is would they have some information about where they are relative to each other? That could be from a camera knowing bearing, what direction are you from me? Or it could be from communication signals that would give you information about how far away someone is from you.
Okay, so let's talk about the aspect of having multiple vehicles here. What if there could be just one vehicle and it could map on the ground and that would be beneficial to it, right?
Yes.
But here, is it it's just to improve the resolution or to reduce errors that you're having multiple vehicles talk to each other?
Yeah, so in a scenario like we've talked about with multiple vehicles, if they don't have global information and their information about their heading is not correct, then you could think of aircraft thinking they're going one way and they're going another. If you have this sort of information exchange, this relative range information exchange, you can just eliminate that big uncertainty that over time, a small heading error, a couple of degrees of error over a couple of minutes, all of a sudden creates hundreds of meters of error. Yeah. So mitigating that through this exchange of inter-vehicle pose information can be really helpful.
Okay, and you don't want to lose vehicles, you don't want to injure people, you don't want to damage product you're carrying, all these reasons to be careful, right?
Right. Okay,
great. So I've thought of the military and kind of commercial delivery applications. Are there any other uses that have occurred to you that this would be right for?
So I think if you think broadly at any kind of multi-vehicle scenario where you don't have global position information or your GPS type information is degraded, it could be useful in a warehouse, a robotic robot, multiple robots in a warehouse moving product around in a warehouse, for example. They have ways of knowing where they are. There are ways to do that. But if there was a situation where you wanted to be less reliant on built-in sensors and stuff like that, then conceivably I would say this type of information could enhance existing sensing methods.
Okay, and I would think a manufacturer of UAVs for that purpose, like industrial UAVs in a warehouse, they might not want to cater their product or alter their product for every warehouse or have a heavy installation. So why not just have them know how to navigate together, right?
Yeah.
Okay. Terrific. And so that's a scenario where they never have GPS potentially.
That's right. In a warehouse, they wouldn't have GPS, but they could have other types of positioning sensors, but those sensors would be sensitive to the clutter of the environment and things like that. So a lot of the positioning technologies depend on direct line of sight from the vehicle to the satellite, if you will. And if that doesn't happen, then you get degradation. So there could be scenarios where just being able to communicate with other robots in the factory could help them all improve their localization.
Okay. So, and Tim, you've been working on these issues for a long time. So 15 or 20 years ago, you had the Proceras startup. So a great BOE startup that was successful with the Kestrel navigation software that you co-invented, I think you and Randy Beard. And so you've been working on these problems for a long time. What are some of the big challenges? What led you to address this problem?
Well, I think just it's a big problem, particularly in the defense sector. Honestly, in a conflict, a peer-to-peer conflict, the likelihood of GPS being available is small because our peers have demonstrated that they can take satellites out of space, right? Yeah. And so it's anticipated that in a serious conflict that GPS would be eliminated. In that sort of situation, say the satellites aren't taken out, are there ways to spoof satellite signals and confuse devices? And if so, how does a UAV know when it's getting a wrong signal? Okay, that's a really great question. Yes, there are ways to spoof the GPS system signals. And in terms of ways to avoid it, having basically alternative methods. And so I hadn't really thought of this, but the methods we're using could be used as a spoof detection check. If you're getting information, and we have done work like this, where you're bringing in sensor signals from GPS, pseudo-range signals from GPS, and imagery and onboard IMU type sensing information, and trying to figure out what information to incorporate in your navigation solution, and looking at the quality of the signals coming in or the correctness of the signals coming in compared to what you expect them to be. And so that's kind of a standard thing for these navigation solutions. I think you could do a similar thing to try to detect spoofing of GPS. If your inertial measurements don't correlate with what you're seeing from GPS, or if your imagery and the measurements you're taking from imagery are not correlating with what GPS is telling you, then you could potentially flag or that you're being spoofed. Oh, that's super interesting. And it seems to me that the terrain has got to be pretty reliable, right? Yes. I mean, the terrain is, there's a lot of good information in the imagery from terrain. A challenge with terrain is there are seasonal dependencies. Yeah. I mean, a problem that's motivating some of our current work is that some terrain is not particularly feature-rich. If you think of the desert, if you're flying over a large swath of desert, then all you see is sand, salt flats, or the ocean is one of the main ones that the military in particular is interested in. Is how do you do localization, GPS-denied localization when you're flying over the ocean? Well, and I've seen some of your other technologies that have come out of your lab, and it seems like having redundant navigation systems on UAVs is kind of the norm, right? Yeah, sure. So you can imagine someone who feels pretty good about the navigation software they have on a device, but why not add this this terrain-based and swarm-based technology as well, just to be safer? Yeah, I think it might not be something that you'd look at for every sort of case, but for systems where reliability is paramount, that it might be something that would be good to add. And how much processing burden does it put on a device? Well, it's not a small amount, but it's well within the capabilities of the computation that we have, even for small aircraft. So some of the NVIDIA products, for example, they make small kind of embedded computing sort of products with their GPUs that can do a lot of computation in a small package, relatively low power. So it's not an overwhelming amount of computation, and our approach for doing it is done in a way so that at least the multi-vehicle part of it only requires a minimal amount of information exchange. The bulk of the processing done on board the aircraft comes from, if you're tracking visual features and processing visual features, then that's the kind of the heavy lifting. And then the cooperative aspects of it, we're not passing around imagery and things like that. We're passing around just information about the position and attitude of the aircraft and its relative range to others. And so if you look at the total computational burden on a team of aircraft that are flying using visual sensors, it's in the gigabytes over a 10-kilometer mission, for example. But the amount of information that we're exchanging for the cooperative navigation stuff is in the tens of kilobytes. So it's a very reasonable communication burden, very reasonable computational burden. And in the approach that we use, the bulk of the processing, it's decentralized, where each aircraft is doing its own processing to figure out where it's at, and then the collaborative part of the problem is relatively lightweight.
Okay. And I'm of course picturing very resource limited devices like tiny drones or delivery drones or something like that. But what's the largest type of aircraft for which this might make sense?
I think that's a good question, because it depends somewhat on the quality of the onboard navigation systems. Some of the military-grade navigation systems, the best navigation systems in the world, can navigate really well just with accelerometers and rate gyros. They can figure out their attitude super precisely and just dead reckon as to where they're going, and occasionally pick up landmarks and things like that. For smaller aircraft or aircraft that use less affordable sensors, then there's all sorts of errors in those kind of baseline inertial navigation sorts of sensors that they can't be relied upon. And so you have to kind of fold in other stuff. So the largest and most sophisticated aircraft would probably have nice alternatives to what we're doing, star tracking and things like that. But smaller aircraft and even aircraft of significant size, manned aircraft, could potentially benefit from something like this.
Okay, so a small, like a solo two-seater airplane or whatever, this could be a redundant system that kind of helps them stay on course.
Yeah. And of course, there's a long history of piloted aircraft having navigation methods that aren't autonomous, and they have robust systems. So I think I see this more in an unmanned space typically.
That makes sense. Okay, so most tech companies, it seems like a lot of tech companies emphasize their use of artificial intelligence at this point. We've gone through a huge wave of that. Would we call this an AI technology, or what? How is it?
I don't really see it as AI by my definition of things. However, there are techniques where we're talking about localization relative to features and landmarks. There's some very interesting work in what's called semantic simultaneous localization and mapping, so semantic SLAM, where they're actually trying to look at the environment and figure out what's there. In other words, to classify what's there. That that's a tree, that's a building, that's a car, that's a person.
Right.
And then using that additional sort of information to aid the navigation problem. Whereas kind of what we do now when we're talking about features, we're just looking for kind of distinct things, sharp edges, things that are illuminated relative to everything else in the environment. You don't know what it is, but it's a distinct visual feature. And in the semantic slam, they're looking at trying to identify kind of what things are in the environment, whether it's something just like a tree or a car, or perhaps a specific building. And so those sorts of things, I think, add additional information and very much are using like large language models and things like that. So AI.
Okay, great. And help me understand how the feature recognition helps with navigation. So say the devices, the software on each UAV is recognizing some feature and it doesn't know what it is. It's just a dark line that looks like this next to a white space, some kind of marker like that. Does the navigation benefit result from the fact that one UAV has flown through and seen that and now another seeing it and we know that was 0.1 seconds ago, so we must be this distance apart, or how does it work?
Yeah, so it's really, I think, so I mentioned that stuff would kind of sit on top of what we do. I think the underlying mathematics of figuring out where you are maybe wouldn't change so much, but it's the ability to say, I just flew past the red car, or I just saw this big conifer or something, a big tree of this type. And maybe, we're working on a problem, not me per se, but people I work with, working on a problem where you have an aircraft flying over terrain, identifying features, helping a ground vehicle to find its way.
Okay.
So in that sense, this semantic slam or these semantic maps can be really helpful.
Okay. And for this particular technology, when you're researching something like this, and entrepreneurs trying to implement this will want to know, how did you develop the technology? What tools do you use to develop something like this?
So some of the underlying technologies are, different filtering by like Kalman filtering based methods. Of course, more contemporary are graph-based methods. We're doing graph optimization, factor graph optimization specifically. So there's mathematical frameworks that we're building on. We're exploiting, sensor information from sensors that are improving all the time, both IMU, inertial measurement sensors, accelerometers, rate gyros, but lightweight, high-resolution cameras, different types of cameras. These ranging radios that I mentioned are kind of new on the scene and are an important tool in this problem. Onboard computing, there are some requirements, but with the development of modern computers, both memory and computation performance is well within the capability of what we're doing.
Okay, so imagine an entrepreneur learns about the technology and says, well, I want to have UAVs that fly into warehouses, grab packages, then fly and deliver them to people in cities. So multiple situations where you might lose the GPS signal. If someone like that were to acquire this technology and try to implement it, what are the steps or challenges they would face?
Well, that's a really good question. If I'm very candid, taking something from something that's been prototyped and demonstrated to something that's robust enough to work in the real world all the time with great reliability, I think that's a significant challenge. Yeah. I mentioned that, and I can refer to self-driving cars.
Yes.
The technology of self-driving cars has been around a while, kind of wringing out all the challenges and bugs and all there is to go along with that problem has been, I think, harder than anticipated. I think the stuff that we're talking about here could have some of the same challenges. But I think it provides a way forward on problems that, there aren't a lot of solutions for. So.
Yeah, so I was talking to one of your colleagues about Tesla self-driving, which is amazing, but and his take was, 99% of self-navigation you really can program really well. It's that last 1% of unexpected random things happening that's so hard. Will self-navigation, UAVs, cars, or whatever ever get there, be perfect?
Yeah, I think, we're seeing some things now. I think that deploying these autonomous vehicles in situations that are a little better defined and constrained, I think will help us move towards solutions. Like I have students currently who've been working on autonomous trucks, and basically they're doing, leaving from a terminal near a highway, driving to another terminal that's near an exit. So they have a very short distance they have to drive before they get on the highway, and they don't go into areas that aren't well understood. And so in those sorts of scenarios, I mean we'll see these. I think within the next few months, being deployed commercially in Texas and Arizona, where the sun shines a lot and there's not a lot of there is inclement weather in Texas. I know that, but in good weather and good visibility, flying or driving down the right lane of the freeway between exits 250 miles apart or whatever. That's pretty much I won't say a solved problem, but it's in many aspects it's a solved problem. It's now getting it, the final edge cases worked out, and it'll be on the road soon.
Yeah. Well, good. I think it's exciting and great. Well, I know we're about out of time, but Tim, thanks for taking the time. You're very busy, prolific inventor who's done just a lot of great things for BYU and the world. So thanks so much for taking the time.
Thanks for having me, Dave.